So dear students, welcome to the last session of this experiment where we are trying to measure the dispersive power of a grating. And in this section, we'll start with first calculating the least count of the spectrometer. So here is the spectrometer that I have already shown you. And in this case, the measurement is taken by, giving rotation of this telescope in these directions and looking at through the eyepiece here. And when you see a bright line, then you take the recording from this window. This is the vernier scale, and there is another window here. So these two windows are for recording the position of this telescope, right? So what is going to happen is, first we will calculate something called the least count of this window, of this vernier scale. So here the least count is calculated from this vernier scale, and here this vernier scale is actually consisting of two scales. One is called the vernier scale, which is the smaller one, and then another is this circular scale, the main scale reading. So the circular scale is attached with the telescope. So the circular scale here is attached with this telescope, with this frame, and the moment I rotate the frame, then this circular scale here in this window, the lower one, the lower scale rotates, and this rotation I showed you in the last video. So what we are trying to measure is, so that our the telescope, and let's say this is the position for the first line, n is equal to 1 position. So we're trying to measure this angle. So what we'll do is we'll take the reading from this window for the position which is n is equal to 0 here. Then we'll take the reading for the position here, and then we'll subtract the two values, and that's how we'll calculate the angle theta. So for this, first we have to learn how to take the reading. So here what you see, in this case, this is our vernier scale, right? And this is our main scale. So the main scale goes from, it depends on the machine. In some cases it goes from 0 to 180, or in some cases it goes completely from 0 to 360. So if it is going from 0 to 180, then there will be two scales, one going from 0 to 80 and then another scale going from 0 to 180. And if it is just one single scale, the circular scale, this so that's how this ring is. So this is our circular scale. It goes from either 0 to and then complete round 360, or this could be divided into two parts like here. So this is 0, this is 179, then again 0, this is 179. So it depends on the spectrometer to spectrometer. The first thing you have to notice, how is the scale? Is it from 0 to 360, or is it from 0 to 180, then 0 to 180, right? Okay, so in this case we have 0 to 360, and right now for a given position, let's say this position, this is the reading, this is the place of the two scales. So what first you have to notice is that in the vernier scale you have 0 to 60. So how many such these lines? 60 lines are there on the vernier scale, the smaller one, right? And then another thing that you have to notice is, what is the smallest unit that you can measure in this scale? So for example, in this scale, how to find out what is the smallest unit? So this is 90, this is 100. So 90 to 100, in between you have 95. So 1, 2, 3, 4, 5. So this is 91, this is 92, this is 93, and so forth. So from 90 to 91, how many such lines are there, smaller lines? 1, 2, 3. So 1 degree is divided into 3 parts. So what is the smallest unit that you can measure is 1/3. degrees that you can measure in the main scale, right? So to calculate the vernier constant or the least count of this vernier scale, what you have to do, you have to first find out the minimum that you can measure in the main scale, minimum of main scale. And we have seen this, in this case it's 1/3 degrees. Then you have to measure how many divisions are there in the vernier scale, the smaller scale. We have seen there are 60 divisions. So your least count LC is going to be this number, the minimum in the main scale that you can measure, which is 1/3 degrees, that divided by how many readings minimum, how many divisions are there? 60 divisions are there. So your least count is 1/180 degrees, right? So how to take the reading? Once you have calculated the least count, then you can go ahead and take the reading, right? So to do the calculation, what you have to notice is, let's say, so these are various different types of vernier scales that can be attached with a spectrometer. So here, how many divisions are there in the vernier scale? There are 10 divisions in the vernier scale. What is the minimum that you can measure in the main scale? It's 1 degree. So 20 to 30, how many divisions are there? 10 divisions are there. So minimum 1 degree that you can measure. In this case, we have just shown you, this is the least count. So in this case, how many divisions are there in the main scale? It is 30. What is the minimum that you can measure? Again, you see it's only 0.5 degrees. How? So from here, 310. So here is 315. From 310 to 315, you have 10 divisions. 1, 2, 3, 4, and so forth, 10 divisions. So 5 degrees divided into 10 divisions. So how much is the minimum? 0.5 degrees. So for this main scale, this is half this quantity minimum, right? Half degrees. Similarly, for this scale is also 0.5 that you can measure, 0.5 or half degrees. This is 0.5 and so forth. So given a spectrometer table, first you have to, before you take the reading, first you have to see what is the least count. So for that, you have to see how many divisions are there in the vernier scale, 30, 60, something like that. And then what is the minimum that you can count in the main scale, right? And then you take the ratio of these two. And that would give you the least count. Why do you need the least count? Because when you take the reading, then you need this least count. How? Let's say if this was your scale, then the reading for some position of the telescope is, you have to first see where is the 0 line, right, of the vernier scale. So this is the 0 of the vernier scale. The vernier scale just crossed, this is 20, so this is 19. So it just crossed 19, and then this distance is left. So this much angle or the rotation is excess. So you take the main scale reading, here is 19. And then to calculate this rest of the part, you have to look at this vernier scale reading. How to take the vernier scale reading? You look for which line in the vernier scale matches perfectly with any one of these main scale, divisions. So here in this case, it's this, right? So how much is this? So 1, 2, 3, 4, 5, 6, 7, 8. So your vernier scale reading is 8. right? So what would be the total reading? Total reading would be 19 main scale reading plus vernier scale reading multiplied by the least count. So how much is this? Okay, let me change the color. I think blue would be nice, or yellow would be nice. So main scale reading is in this case 19 plus how much is vernier scale reading? It's 8. Least count is how much? 0.5 divided by how many divisions are there? 10 divisions, right? So then you take the sum, whatever it is, that's your total reading. That's the position that this vernier scale setup is telling you for the telescope. Similarly, from here, the 0 of the vernier scale, so this is 250, then this would be 245 here, so this would be 244, so here is 244, so it just crossed 244 and then 44 point how much? 1 1. So first line it crossed, right? So that you take and then you find out which one of these vernier scale matches with this main scale. So in this case I have looked carefully, so this is the reading. So this is 50, 51, 52, 53, 54, 55. So 55 would be the vernier scale reading. Main scale reading would be 244. Okay. So that's how you, and then you can calculate the main scale reading. The sum of main scale reading, total reading would be main scale reading plus vernier scale multiplied by the least count for this. And we have just calculated below the least count for this scale. Similarly, you can calculate the least count for these scales too. So in our case, the least count is 180. Now, what are the working formula that we have to remember? In a few lecture back, or the few videos back, I showed you for our diffraction grating, the grating element, which is A plus B, is 1 over 30 millimeter, 1 over 300 millimeter. The grating equation is this. And then in this experiment, you will see that we will be calculating the wavelength, which is derived from this grating equation given by this. So wavelength can be measured based on what the position of the diffraction line that you are seeing. So you calculate the theta and then n is equal to how much, and then you take this, calculate this the wavelength from this formula, and then the dispersive power can be calculated from here. Again, only you need theta n and a plus b. A plus b is fixed. So now we are going to calculate theta for different n values. N means which one is the line, right? So if you remember here, n is 0 for the center one, the direct line that you see, and then as you rotate, n gets increased on the both side. Here the plus and minus are just to show, differentiate between which side you are taking, right? How you measure the angle. Now here is a typical table that you would take. Here first is the n, the position of the image, the central one, the first on the right, second on the right, and then first on the left, second on the left. Then for all these positions, I have calculated the main scale reading and then vernier scale reading and the total scale reading, right? So again, remember, total is how much? Total is main scale reading plus vernier scale reading multiplied by the least count. So that's how I got these numbers, right? So once I have calculated this total readings, means the position of the central, first right, second right, first left, second left, right? So please do remember this configuration. So then once we have these readings, then I can calculate the theta. Theta means what is the angle through which I have rotated my telescope for going from the central line to the first line that I see. How much? You take the difference between these two numbers. So you get this. Then to calculate how much rotation I have to give to go to the second on the right, I have to take the difference between these two, and you get this number. Then on the left hand side, you have to take the difference between, for n is equal to -1. You have to take the difference between these two. For n is equal to -2, you have to take the difference between these two. Right? So this difference gives you this number. This difference gives you this number. Right? So this is also n is equal to 1. This is n is equal to -1. This is n is equal to 2. N is equal to -2. So basically these two ideally should have come same, but they are not, and that's where the experiment comes in. In experiment, you don't get everything what you expect. You get a little bit of error. So n is equal to 1, angle is calculated by taking the average of these two, this and this number, which is done here. For n is equal to 2, we calculate the difference by taking the difference, the average between these two numbers, right? So which is calculated here. So for n is equal to 1, the angle is 10.1. For n is equal to 2, the angle is 20.542, something like that. And then once you have got n and corresponding theta values, then you can calculate the wavelength. So here I have done, for n is equal to 1, I place this theta 1 here, and n is equal to 1. I have calculated the angle, the wavelength here. For the wavelength that you calculate for n is equal to 2, it turns out to be a little different. Ideally, this should come out same, the same wavelength or the same light, sodium light that we used. But you see, there are some differences, and these differences are due to your error in performing the experiment. And for any given experiment, error are always there, but your aim has to be like you always try to minimize those error, right? So how much is the error here? If you remember, the lambda, the wavelength for the sodium light is 5893 angstrom, and in this case we have got a little bit different. So from here you can calculate the percentage error that you get for the measurement of wavelength. Okay, so that's one side result of our experiment. Next, the dispersive power. The dispersive power is given by this formula. So for n is equal to 1, a plus b cos theta, theta is 10, and the dispersive power is this. For n is equal to 2, dispersive power is this. So what you see, the same grating has different dispersive power for different n, for different positions. So the more the n value, or the you go away from the central line, the dispersive power increases, right? That one conclusion that you have to take, and that goes like something like more than double. In this case, it's 304, 640, it's more than double. The n became 1 in this 304, and n is 2 in this 604. So it's more than doubled, while n only doubled. So n is equal to 3 and 4 for other grating elements. We couldn't see n is equal to 3 though in this experiment. And actually, what is the maximum n value that you can see? You can calculate it from here, from this expression actually. The lambda you know, and then the a plus b we also know, and then inversely then you can calculate, because this theta can never go beyond 90. So from there you can calculate the maximum value of n that you can see. Okay, so that ends this experiment. So in this part, what we have looked at, first we have calculated the least count. I have shown you how to calculate the least count, and we have calculated the least count to be 1 over 180, and then you take the reading for different position of the telescope for given the line that you see, first line, second line on the right hand side, first line, second line on the left hand side, and then the central line. And this is your, the main figure that you have to remember. So this is the table. Once you have got the table, then you can calculate the theta for given n values. You take the difference between these positions with respect to this center, and from that you can calculate the wavelength of the light that was used, and it doesn't come out as it should, and that's the error part. You have to calculate how much was the error in our experiment, and then we have also calculated the dispersive power of the grating for n is equal to 1, for n is equal to 2. Right, so with this we have come to an end for this experiment, but I would leave you with some homework questions. Here are the some positions of a vernier scale. So this is not a circular scale, this is a linear scale anyway, but this again would give you some idea. So here you try to calculate the total reading of this vernier scale. Again, what you have to first find out, you have to find out the least count of this vernier scale. It's the same vernier scale, so it goes from 0 to 50. So how many divisions are there? 50 divisions are there. And then what is the minimum that you can get here? So the minimum is 35 to 50, so it's 0.5. 0.5, let's say this is in cm, this is in millimeter. So 0.5 millimeter, and then you have to calculate 0.5 by how many? 50. So the least count is 0.01, right? And then, for example, the main scale reading in this case, it's exactly 0. Main scale reading is 10. The vernier scale reading is 0, because 0 matches with this 10. So here, so in this case the main scale reading would be 20, 21, 22, because the vernier scale 0 just crossed 22. So 22 is the main scale reading. Vernier scale reading, you have to find out which one match the best. I would go with this. So that's the vernier scale. Similarly, here you will find out 14, 15, 16, 16.5 is the main scale reading, and vernier scale reading would be, try to find that out. So take that as a homework and brush up your skill for taking a reading in a vernier scale. So thank you very much. We conclude with this.